Sensitized solar cells part 2. Hello, welcome to D Creations Resources. We've already talked about the construction aspects and working aspects of dye-sensitized solar cells. So they differ from conventional semiconductor devices because in them they separate the function of light absorption from charge carrier transport. So we know that there are two important functions here. Light needs to be absorbed and the charge carrier created need to be transported. Dye sensitizer absorbs the incident sunlight and exploits the light energy to induce vectorial electron transfer reaction. So dye sensitized solar cells do have some advantages when compared to silicon based photovoltaics. First of all, it's not sensitive to the defects in a semiconductor, like for example defects in silicon. Also, DSSCs are easy to form and they are cost effective for production. Thirdly, it is possible to realize the direct energy transfer from photons to chemical energy. The earlier photochemical studies of dye sensitization of semiconductors focused on flat electrodes, but these systems were facing an intrinsic problem. Only the first monolayer of adsorbed dye results in effective electron injection into the semiconductor. But such light harvesting from a single dye monolayer is extremely small. By application of nanoporous TiO2, the effective surface area can be enhanced 1000-fold. That's why the importance of TiO2 in case of dye-sensitized solar cells. In fact, solar cell based on a dye-sensitized porous nanocrystalline TiO2 photoanode, which performed very well, was first reported by Grätzel. So this was about the importance of TiO2 in it. Now to talk a little bit about the historical aspects. In the late 1960s, it was discovered that electricity can be generated through illuminated organic dyes in electrochemical cells. And at the University of California at Berkeley, chlorophyll was extracted from spinach. And first chlorophyll sensitized zinc oxide electrode was designed. It was in 1972. So for the first time, through electron injection of excited dye molecules into a wide band gap of semiconductor, photons were converted into electricity. But the efficiency was poor, so in order to improve that, porosity of the electrode was optimized so that the absorption of dye over electrode could be enhanced, and hence the light harvesting efficiency would also be increased. So Grätzel cells were co-invented in 1988 by Michael Grätzel and Brian O'Regan, and here nanoporous titanium dioxide electrodes with a roughness factor of around 1000 were discovered. The efficiency was around 7%. So there was further development and the efficiency had to be increased. So Grätzel and O'Regan fabricated a device based on a 10 micrometer thick high surface area and optically transparent film of TiO2 nanoparticles coated with a monolayer of a charge transferred dye with ideal spectral characteristics to sensitize the film for light harvesting. So in DSSCs, the role of semiconductor is different. In a traditional solar cell, silicon provides two functions. That means it acts as source of photoelectrons and also provides electric field to separate the charges and create a current. But in dye-sensitized solar cells, the bulk of semiconductor is used as a charge transporter and the photoelectrons are provided by photosensitive dyes. Now again, to remind you of the construction and working of dye-sensitized solar cells, the four key parameters for DSSC are the working electrode, sensitizer, that means the dye, redox mediator, which is the electrolyte, and counter electrode. So in other terms, dye-sensitized solar cells, it's an assembly of working electrode soaked with a sensitizer or a dye and sealed to the counter electrode, soaked with a thin layer of electrolyte with the help of a hot melt tape or to prevent the leakage of the electrolyte. Now, the DSSCs are typically constructed with two sheets of conductive transparent materials which help a substrate for the deposition of the semiconductor and catalyst, acting also as current collectors. So there are two main characteristics that a substrate should have. Firstly, more than 80% of transparency is required by the substrate, of course. Transparency to what? Transparency to permit the passage of optimum sunlight to the effective area of the cell. So the sunlight needs to pass through. Transparency is a key. And secondly, for the efficient charge transfer and reduced energy loss in DSSCs, it should have a high electrical conductivity. So both transparency and conductivity need to be there. The fluorine doped tin oxide and indium doped tin oxide. So the short forms, of course, for fluorine doped tin oxide is FTO. It's SNO2 and fluorine F. While in case of indium doped tin oxide, it's ITO, N2O3 and SN tin. Now these two are examples of TCOs, transparent conducting oxides. So TCOs are an important aspect of solar cells, and as mentioned earlier, they need to be transparent as well as conducting. Let us try to talk about TCO. So transparent conducting oxides, as the name suggests, these are electrical conductive materials and they have a comparatively low absorption of light, because there are two words here. Conducting, so obviously it has to be electrically conductive, and transparent, that means the absorption should be as low as possible. It should allow the radiation to pass through. Now, of course, we are talking in connection of solar cells, so we are talking about the solar radiation, and so it has to be a layer which will allow the solar radiation to pass through. So typically these are prepared with thin film technologies, and they are used, like along with solar cells, they are also used in optoelectrical interfaces, displays, etc. Now there are materials which have one of these properties. For example, if you consider glass fibers, they conduct light. It's almost lossless conduction of light, but they are electrical insulators. So they are not electrical conductors. So here comes the significance of TCOs, transparent conducting oxides, which have both the properties, and in fact these properties are also tunable. You are able to tune the conductivity as well as transparency. Now these TCOs can be binary compounds, or they can also be ternary and quaternary compounds. One of the most prominent example of TCOs is ITO, indium tin oxide. When they are used in solar cells, they are basically playing a role as a back or front contact electrode in, say, silicon heterojunction solar cells. So ITO, for example, can be used as TCO material to improve the efficiency of these solar cells, because they have excellent physicochemical properties, like they have high transmittance and electrical conductivity. Band gap is also high, but the refractive index is low. So if you say D is a dopant, then you can have a general formula AyBz:D. Now, indium tin oxide that we talked about, it's a solid solution of indium oxide, which is In2O3, and tin oxide, which is SNO2. And the ratio is typically 90% by weight of indium oxide and 10% by weight of tin oxide. It is transparent and colorless as a thin film, and as a bulk material it is yellowish to grey. Now this is preferred so widely because it has two important properties, of course, related to its electrical conductivity and optical transparency.